I will provide you first an overview of the ns-3 simulator. So what is ns-3? ns-3 is, well, first of all, a discrete event simulator which is opposed to other kinds of simulators such as discrete time simulator, and then it's a network simulator. So in general it's a simulator that is meant to simulate complete communication systems. Well, and what do we mean with complete? Well, we mean in general including detailed models from layer 2, so MAC layer, to the application, up to the application layer. And for the physical layer, it is typical of a network simulator, and it is true for ns-3 as well, that the physical layer is modeled in a simplified fashion. And this is normally because of scalability issues, that if you want to simulate a very large network, you cannot afford to have a very fine-grained detail at the physical layer. And in network simulator in general, and again this is also the case for ns-3, the granularity of a model is the packet. So the event that is typically simulated by the simulator is the transmission of a packet, reception of a packet, interference between the transmission of the packets, and so on. But this is kind of a general statement. From a practical point of view, there are different models provided by ns-3, and different models could have a different understanding of what is a packet. I mean, for example, a packet at the IP layer is different from a packet in LTE at the RLC layer, for example. And so actually the granularity of the simulation can be different depending on the model because of this.
So,
yes?
sorry, it's impossible to simulate a new MTS network here because of it's focused, well, as I understood, it's ns-3 is focused in the IP networks.
No, it's not true. There are models for wireless networks as well, like we are building an LTE model. There are already models for WiMAX and for Wi-Fi, and not in ns-3 but in other network simulators that have the same packet-based approach. You can find also UMTS models. So the way this is done normally is that you still maybe use the packet as the fundamental unit, and then you actually map the packet to a waveform that is transmitted over the air. And in the case of wideband CDMA, it would, for example, calculate the interference with that and model in this way the transmission.
So the packet is the basis, and to simulate a UMTS, for example, we have to find an approach or something like this.
Yeah, actually there are, it is more like a common approach that is used with ns-3, but it's not enforced so much. Okay. So you could have one component of the simulator that simulates on a finer grained resolution. For example, there is one particular version of a Wi-Fi model that has actually a complete signal processing model implemented inside the model. So when you run ns-3, of course at the IP layer you will see packets, but below, whenever one transmission attempt is done, there is a whole signal processing implemented. The thing is that, for example, this particular model is very slow to execute and can only scale up to a transmission with a few nodes. So the reason why normally you don't find a complete signal processing model in network simulators is just because of scalability. It's not that it's impossible to do it, but it's not the focus here. People that are really more interested in signal processing, well, normally they prefer MATLAB. And they can do other type of simulation and other type of evaluation. Okay, so then ns-3 is not only in general a simulator, but it's also a collection of simulation models, and there are several models that allow the simulation of different things. For example, we have different models for some wireless technologies. For some wired technologies, we have models that allow to simulate different protocols and different applications and so on. We will see some details afterwards. ns-3 is also a free and open source software project. so that is using the GPL version 2 license, and that has a community of developers and maintainers and of users as well. And the users normally are, say, two kinds of users. On one side, we have educators and students, like people at the university that are giving a course on networks or on wireless technologies, and they want to have the students learn how these technologies work, and they use the simulator for that. On the other side, we have researchers that want to, for example, evaluate the performance of some algorithm that they are designing, and they use the simulator for this purpose. And well, from a high-level design perspective, ns-3 is modular in structure, in that it's meant to be easy to add new modules and that implement models, for example, a new wireless technologies, a new application, and so on. And the core of ns-3 is designed with one very clear objective, which is to be aligned with a real-world system. And in particular, the reference of real-world system is, say, Unix, Linux machines and operating systems. And we'll see afterwards in detail what I mean with this. And another high-level design feature of ns-3 is that it's put a strong emphasis on integration with the real world, which means in particular that since the beginning of the development of ns-3, which happened around 2006 more or less, one of the goals was to support emulation mode, that is running the simulation with a real-time clock and having the simulator transmitting real packets over real network, talking to real hosts and real application. And the other item was real code integration, like being able to actually link real application binaries, for example, with the simulator and interacting. And we'll see also examples afterwards. And from a software design point of view, ns-3 is written in C++ with optional Python bindings. So you can use Python for writing a simulation program if you wish. If you don't like, you can just do it in C++. And it has some highly optimized features. At least the core of ns-3 has these features. And for example, it uses copy on write semantics for the handling of packets. As I said, a packet is a fundamental entity in ns-3, so it is very important to be efficient in handling that. Because of this, or thanks to this, ns-3 has been reported to be faster than many other simulators. Well, especially it has been tested against other freely available simulators such as ns-2, and it has been reported to be faster and to have a smaller memory footprint. And well, then it has other features, well, commonly found in lots of open source projects. You find that smart pointers are used, even though they are not natively provided by C++, so ns-3 does the same. And also ns-3 uses its own object framework on top, of course, of the of C++, which is itself object-oriented. And the aim of this object framework is, well, there are several aims. One of them is to solve, for example, the object composition problem, so to allow to compose arbitrarily objects of different kinds that possibly, in a way that possibly was not foreseen by the original developer. And from a maintenance point of view, so regarding a bit more how the ns-3 is organized as an open source project with respect to the community of developers, well, code that is developed for ns-3 and it is accepted in the official ns-3 release needs to comply with a well-defined coding style. And before the code is accepted, there is actually a code review process which is done by the community of developers. And normally the code is iteratively refined several times before it is accepted. And finally, there is a strong emphasis on testing for all the code that is officially maintained in the ns-3 distribution. And if you want to use ns-3, so there are actually two kinds of APIs that ns-3 offers. So the first one is the high-level API, which is basically the API that you would use if you are like you want to run one simulation and you want to create a particular network topology. In that case, you would use these so-called helper objects that allow you to create this topology and to run the simulation. If, on the other hand, you want to develop a new model or improve an existing model, then you would use the low-level API. That means APIs that are defined between specific objects in order to implement additional functionality. And actually, the high-level API is rather consistent among different modules, whereas the low-level API is really specific to the model that you are dealing with. There are some common traits among different ns-3 models, but they're not so much enforced because of some models can be really be so much different from others. And well, important things to mention. Well, I will talk about the configuration system later and tracing system as well. It's important to mention that there is no official IDE for ns-3. Many many developers use Eclipse with satisfaction. I am not, for the record, but in general, so you just have to choose your IDE, maybe the IDE you are already used to, and help yourself, basically. There is also no official GUI. So there are some of them. I also have a slide afterwards explaining it, but there is no official one. It means that normally ns-3 is expected to be executed from the command line. And if you want to write, to create one simulation, you have to write one simulation program. This is the way in which simulations are run. And having a look at the modules that are included in the official ns-3 distribution, you find two categories of modules. First one is the main modules, which is core network, internet, and applications, which are used more or less in all simulations. And then there is a lot of other modules that are very specific, and you normally use it or not, depending on the particular scenario you're simulating. And normally, the way you set up a simulation is like this. So you create, first in your simulation program, you first use some instruction to create some nodes. Then you use other instructions to interconnect the nodes so that they form a network. And typically this is done using objects of one kind, which is called channels, so that you can connect the nodes via channels. And then you configure the network topology. You create some instances of application, and then configure these applications so that they will generate some traffic that will be sent during the simulation. Finally, you give one instruction to start the simulation, and when this instruction returns, the simulation has ended, and you can collect output. Well, I forgot to mention that you also have to configure the simulation in order to generate some output. Output is in several forms. There are, like, it depends also on the model which you're using. Often you have trace files, that is big text files with lots of data. You can also directly gather some measurement within your simulation program. There are means for doing that. And as I said, in general, all simulations use the core network, internet, and application module because they are needed to do something like to send traffic and to have nodes and so on. And plus, you normally put some device module that, depending on the technologies that you want to use. If you want to do a simulation with Wi-Fi, you will need the Wi-Fi module. If you want to use LTE, you will use the LTE module and so on. And I'd like now to explain a bit what is the concept of a node in ns-3. You can think of a node in ns-3 just as a container, like the case of a computer into which you plug different items, and these items are of, in general, of three different kinds. On one hand, you had network interface cards, so like devices. They are normally called the devices. Then you have the IP stack, or well, a networking stack. You could actually run simulation without IP, but with a simplified network layer stack. And then you also plug applications, and all this together build up a node. So this is very generic, and in fact, if you have a look at the types of things you can do with a node, well, a node can be everything from a base station to a mobile phone to a laptop, a router in the internet, or a sensor node, and this all depends on what you put inside a node. And the model of the node in ns-3 is inspired from a real system. This is a key difference with respect to other simulators, such as, for example, ns-2, that had a completely different node model. And in particular, like the interface between the applications and the networking stack was modeled after the sockets interface. And the interface between the networking stack and the equivalent of the network interface card was modeled after Linux net devices. And this, well, apart from being easy to understand to people that is familiar with these concepts, also has the additional benefits that it makes it easier to reuse existing application code or also kernel code inside ns-3. And there are other models that can be used inside a node which do not fit into the category that I explained before, and examples of these models are, for example, the mobility model that keeps track of position of the nodes in simulation, or the energy model that keeps track of how much energy is consumed by one node. For example, if it's a mobile node with a battery, we want to be able to simulate the fact that the node might eventually run out of battery. And here is a picture that describes the architecture of the node. Again, it is evident here that there are applications which can be of different kind. Then we use sockets to talk to the networking stack. And then below the networking stack, we have devices which can be of different kind. And in this example, we see that there are like Ethernet devices, LTE devices, and Wi-Fi devices. And for every specific kind of device, normally there is one corresponding model of channel. Like an Ethernet device will have a corresponding Ethernet channel model implemented in ns-3, and the same for LTE and for Wi-Fi. There is actually one exception in ns-3, which is the so-called spectrum model, which provides actually one type of channel which can be used with different wireless technology so that they interfere one over the other. You could think, for example, of doing a simulation in the ISM band with both Wi-Fi and Bluetooth interfering on top of each other. In that case, we want that the instance of the channel which is simulated in ns-3 is the same, so that we can actually compute the interference between different technologies. And actually, the implementation of the LTE model that we did in the LENA project is using this particular implementation of the channel. And a list of available net device models that you can find in ns-3 are in this slide. And the most used are definitely the one on the left-hand side, like point-to-point devices, like wired links, or CSMA, which is a model which is normally used to model Ethernet networks. And then we have Wi-Fi, WiMAX, and LTE. These are by far the most popular. Then there are other models which are a bit more exotic, to say. I'm not sure how many people of you are interested in simulating underwater acoustic network, which is the case of the last model here. But I mean, there are models for these very specific scenarios. And actually, some of the models on the right-hand side are really commonplace even in real system, like the loopback device. You normally find it in real system. Its actual usage in simulation is a bit limited because maybe people is not so much interested in simulating this, but anyway, it's available. And about the possible applications, well, there are not so many. If you just have a look at the list, maybe you can think it's a bit short. But the fact is that there are some models which are very generic. For example, the on-off model has a lot of configuration parameters which allow you to basically have different traffic patterns. And for example, you can configure it to send traffic which looks like voice over IP traffic or video traffic and so on, just by using different configurations. Bulk send is an application model which is meant to be like a bulk file transfer and is normally used on top of TCP. Then there are some other models which are used for UDP traffic. And in the case that this is not enough, well, first of all, it's fairly easy to write a custom application model that generates traffic according to your pattern. And then you can, two alternative solutions that do not rely on ns-3. First, you can use the DC framework, which stands for Direct Code Execution Framework of ns-3, and which allows you to basically link a real application with ns-3 and use that application to inject traffic. And this has been done successfully, for example, with the popular VLC video client. And another alternative, you can actually run the simulation in emulation mode and connect it to a real node with real application inside via, for example, an Ethernet cable. And in that way, you could inject real traffic into the simulation and simulate some part of the network that responds to your configuration. And an overview of the networking protocol that are available in ns-3 is in these slides. We support both IPv4 and IPv6. From the transport protocol point of view, we have native ns-3 implementation of UDP and TCP. That means that some developers re-implemented, for example, TCP in ns-3. And as you can imagine, this implementation of TCP has some differences with actual implementations that are used in a real system. And for this reason, actually, there is another possibility in ns-3, which is to use real TCP code from the Linux kernel. And this is done thanks to the so-called network simulation cradle, which is a framework which is listed here, and the acronym is ns-3. And then there are also several routing models that you can use with ns-3. Well, of course, there are some. You can use static routing in ns-3, and then a lot of routing protocols which are typically used in the context of ad hoc or mesh networks, like AODV, DSR, DSDV, and so on. When it comes to doing a simulation with wireless network, the typical approach is, well, you use some net device model that models some wireless technology. This is obvious. And then you use the mobility models, which allows you to, well, not only keep track of position of nodes in in some area, but also to orchestrate the movement. There are different mobility models that allows you, for example, to move users with a constant speed and direction, or to have some random movement according to a pattern, like there are some very popular models with respect, like random waypoint or Gauss Markov mobility and so on. And several models of this kind are available in ns-3. Then, for wireless network, you have to use a propagation model, which is normally inserted into the channel object and is also normally device independent, so the same models are used for different wireless technologies. And this allows you basically to determine how much power is received from one node when another node transmits. And then there are normally error models that allow to model the fact that when you transmit over a wireless channel, often transmission is not successful. And the actual error models is specific for every type of wireless technologies. Like Wi-Fi has, well, actually two different models that you can choose. LTE has other models, like we have one model that we developed for the LENA project. WiMAX has a completely different model, and so on. Here is a list of the propagation models that are available within ns-3, and on the left-hand side you can see frequency flat models, which means that for every transmission it is assumed that there is just one path loss value, or, well, actually path loss, yes, there is one attenuation value that is evaluated. In the majority of cases, this is the path loss. Like we see all these models here are path loss models, but actually there is also a fading model that is working with just a single frequency, and it's an implementation of the Jake's model. And then there is actually the possibility of having frequency selective models. That means that in this case, one particular waveform is not considered to just have one value of power which is constant in the whole band of the signal, but rather there are it's like a vector of values for different frequencies, which could be, for instance, subcarriers in an FDM systems or resource blocks in an LTE system. And there is one particular implementation of this frequency selective model, which is normally used for frequency selective FEDI.
Cool. I have maybe a silly question. You have talked about mobility patterns.
Yes.
Can we show that patterns in a map?
In ns-3?
Yes.
Yeah, I think that there's a form of output. I think there are actually several ways of doing it. There is one way of having an output of, well, not only the position, but also the movement of nodes according to a given trace pattern. And then I think that as an input-output format of ns-3, it supports also the format of another simulator, which is ns-2, which defined a specific format for the tracing and
what I meant is to have
seeing that graphically.
Well, I don't mind to see graphically. If I set a pattern of mobility,
yes,
and then but in an environment, I mean, here we can imagine like a layer of a map with vectors of this is a building, this is a building, this zone is a building, and this zone like a vector. Information shown in a vector that indicates the heights of the obstacles or mountains or something like this to have a map of propagation
of like terrain information.
Yeah, correct.
Okay, so what we did within the LENA project, we developed one specific model for buildings.
Okay.
And this is now part of ns-3 and actually can also be used without the LT model. It's kind of an independent model. And this is actually specifically targeted, so it's just aimed at having buildings, not supporting mobility currently, and the aim was to be able to simulate the like path loss, especially the wall penetration loss.
Okay.
This is what this model is used for. I know that there has been one, beta version of a model, of a propagation model that is using terrain information. I think it's a Longley Rise.
DTM? Digital terrain model? Well,
I think it was Longley Rise. I'm not sure if I get the acronym correctly. And what I know of that model is it's a model that uses terrain information in order to calculate the loss between 2 points. But I do not know the details of that model, frankly. And in general, I would say that this, terrain or map information has to be specific of some other model. So there is no standardized way of doing this in ns-3. There are just some models that, for specific purposes, can support this. And so, one question when working with the simulation, and especially when developing new models for a simulator, is why do we need to basically re-implement something that already exists? Specifically, consider how many open source implementation of protocols already exist. Why do we need to re-implement that in the simulator? Well, often in other simulators this was needed just because of incompatibility between the two things. And in order to address this problem, actually ns-3 focused on some specific aspects. And the first aspect is to try to use as much as possible standard formats for input and output, so that we can reuse some existing tools. One specific case in which this happened and was actually very successful is that of pickup trace output. So ns-3, a lot of models in ns-3 support pickup as an output format, so that you can reuse a whole range of tools that are available, for example, from the open source community, in order to visualize pickup traces, to process them, to calculate statistics, and so on. It is fairly typical to run a simulation with, well, either Wi-Fi or other technologies in ns-3, and then open the results with Wireshark, for example. And the other approach which has been done, which I think I already mentioned before, is that of integrating real code with ns-3. And I already mentioned the network simulation Cradle, which allows to run the TCP code of the Linux kernel inside ns-3. And the other item is direct code execution. I think I also mentioned this before, which allows to link binaries with ns-3. And this can actually be done not only for user space binaries, so application, for example, but also with kernel code. And actually, at the current state, I think that network simulation cradle in ns-3 is a bit deprecated because it has some limitation, like you cannot have more than one net device in a node if you use network simulation cradle, whereas direct code execution is becoming the most popular item even for when it comes to reusing kernel code. Like it has already been used to for example, to reuse the routing protocols implemented in the Linux kernel in ns-3. And ns-3 has an attribute system that has the objective to allow users, so people who want to run simulation, to configure the simulation easily and to save configuration in an easy way. And the way it is done is that every object in ns-3 has additional semantics which are used to define attributes, to give them some description of the attributes, to give default values to these attributes, and to allow the user to set the attributes, the default values via command line. Also to allow to get kind of a snapshot of a configuration, including all the instances of all the objects in the simulation, save it to a file, recover it, and reconfigure it. And there is also a GUI that is used for this, and it's seen in this slide. It's a kind of simple GUI based on GTK, but it does the job very good. So it allows you to browse the hierarchy of all objects and all instances that are created in the simulator, and to go to see the parameters and to set them. So probably if you need to run large simulation campaigns, you will not use this for every repetition of the simulator because it's just too cumbersome. But to, for example, to construct an initial configuration of your simulation, it can be a very useful tool. And also just to browse the possibilities that you have a configured object can be very useful. And as I said, there is no official GUI, but there are a lot of graphical tools which can help you with specific tasks. Well, this one I already shown here. Then here you just see Wireshark, which is, as I said, you can use. Then there are a lot of visualization software that can visualize, for example, wireless topologies here in this figure, or very specific wired network configuration. This looks like a graphical application that was available for ns-2, which was called NAM, and this basically does something similar. And there have been also some attempts of having a graphical tool that can jointly show the simulation topology and allow configuration. Like the idea of this tool, which I'm not sure about actually its current development status, but at least a beta version is available. But this tool allowed you to, the idea was to click on a given icon on the map, which represent a router or a node or something else, and then a context menu would open, and then you would be able to configure it. And about documentation, ns-3 comes with lots of documentation. So there is a manual of ns-3 which basically documents the core of ns-3. Then there is another document which is the so-called models library documentation, which includes documentation of all the other modules beyond the core. Like you will find documentation for the LTE module, for the Wi-Fi module, for different applications, for propagation models, and so on. And finally, there is the API documentation, which is maintained together with the code and is generated automatically using Docker. And all this is available on the web for every different version of ns-3. You will find the corresponding documentation, and you can also regenerate it from the source code. And there are other resources that can be used if you are interested in using ns-3. There is an official ns-3 tutorial. There is a wiki page with lots of how-tos and other information can be useful if you are interested. There is a mailing list which has, I would say, a lot of traffic by people that have doubts on how to use ns-3. If you want to do something in ns-3 and you do not know how to do it, you can always post a message to the list and often you would get an answer for that. And then there is another mailing list which is used by developers to interact for development purposes, for maintenance of ns-3, for doing reviews of the code and so on. And that's it. So that's in the second part of the talk. So what is the time now?
Do you think it's easy to learn, to start with ns-3?
Yeah, it has a learning curve, of course. So it's not that if you start from scratch in one day you will be able to run a very complex simulation. No. I think the most important factor is to be familiar with C++. Well, actually, maybe I say this because I've never actually used these Python bindings. So maybe if you're familiar with Python, you can do simulation. If you're familiar with C++, definitely you will get something out of it. If you, it can take, running some simple topology with existing modules as is, maybe it can take, say, 2 or 3 weeks to get familiar, and a bit more if you want to run very complex topologies and you need to get measurements that are a bit complex to obtain. If you need to develop some algorithm on top of ns-3, it can take a bit more, or if you need to develop a new protocol for ns-3, this can be very complex. But then it depends on the type of model that you want to develop.
Even if you only want to make some high-level simulation, you have to code in C++.
You can. Well, this is one option, or Python. Yes, there is no option to do that without.
Even with a graphical interface.
No, so far not. Okay. Well, there are lots of existing examples that can help you. So I will show you one example. Well, not of the code actually, but of the one scenario that, for example, we ship with the LTE module. And there are many examples for other modules as well, like Wi-Fi has lots of examples. So if the type of scenario that you want to run is very similar to an existing one, then it's probably rather easy to modify it and to get what you want. If you need a very highly customized topologies that has no similar example, then it will take you a while. Overall, I would say that most of the problems that people have in configuring simulation is actually a networking problem. So again, if you are familiar with configuring hosts in a network, assigning IP addresses, defining port ranges, and so on, then it will be easy for you to set up a network inside ns-3, because in the end, a good part of the burden of putting together an ns-3 simulation is network configuration. And actually, the majority of bugs, like people that is trying to simulate something and that sends a message to the user mailing list like, I do this and I don't see any traffic and so on. It's a majority of cases, it's like wrong IP address, or you forgot to specify the ports appropriately or something like that.